Right, so now we're going to work with the first topic of term 3, which is functions. And functions is by far the most important topic in maths because it basically provides the visuals to these numbers. Now, numbers on their own can be very abstract. And this is the reason why, if you're a visual thinker or you like to have many confluences to get to the same answers or many different ways to get to the same answer, that's the reason why we use functions. Because functions provide a much more anchored way of getting to the answer because you can actually see what the number is trying to communicate with you. And so all of these functions, and we will not go into so much of depth with functions at grade 9, right? Because at grade 10 is where we actually delve deep into these ideas. But the only function that we will work with is the linear function, right? But we have to understand the thought process of it, right? Because we do get what we call a quadratic function. So when you did a quadratic equation, that'll become a quadratic function. When you all did exponential equations, it'll become an exponential function. And so this is why when you look at expressions and equations, any expression in any equation, it's actually a function. And I'll delve deep into exactly what I'm saying. So this is why I started off with this mind map. Okay? So if functions are that important, let's understand the basic definition of it. Now, this is not a formal definition. It's just a basic definition. What is a function? A function is a rule or relationship that links each input to one output. And so the most common association with functions is the spider diagram, right? Where you have x as your input, you have some rule applied to that input, and then it gives you what we call the output, right? We can delve deeper into the idea, and if you decode this here, it says it links each input to one output. And so at the higher grades, the thing that you must remember is that whatever number I input here, whatever number I decide to input as x, as long as that number has only a single output, then we can call this here, the rule, the function. It's called the function. Okay, or we can call it a function. Understood? So as long as you're putting an input that will give you a single output, right, then you can call this rule a function. And so the most common way you would see it is y is equal to 2x plus 1. If I input any value here, I'm certain that I'll output a value that will just be a single value. So there's no way that I can input 5 in here and the y value will give me 7 and 8. I'm just saying, for argument's sake, right? It'll give me 2 outputs. There's no way. Because you know you input one value, you're going to get a output of a single value. So for every input, there's what we call a unique output. It has to be unique. Okay? So let's define some terminology. The input is the value you give to the function, right? It's often what we call x. So we input x, right? That's called the input. That's why we call it the input. The output is the result after applying the rule, right? Or the function. After I apply this function to that input, what I get out is what I call the output. Now, more formal terminology and more relevant terminology at higher grades is what we call domain and range. It's the set of all possible inputs, and range is the set of all possible outputs, right? And so you'll see when we do questions at the end, I give you examples where we will work with domain and range. So the domain is the set of all possible values that you input into the function. And so I just want to expand your mind here, but right, we're going to go back to the term 1 topic of number systems, right? I can input any imaginable value in here and I will get an output, isn't it? And so what we can say is that the inputs for x can be any real value. Remember, we did real numbers. And so if you start from the top here, real, we add non-real, and then it branched off, isn't it? So we can't input non-real values because non-real values do not exist, isn't it? They are imaginary. So this is why we say we can input any real value, and we use the sign here called element of, right? So x is an element of the real number system. Okay, that comes more from sets, right? When you talk about a set, right? The way I think of it is exactly like this here. There's a container, and in this container we have every possible imaginable real value that can be in this container. And so when we're saying x is an element of, when we're saying element, it means it's a member of the set, right? It's a member, or it's a element of the set. So everything that lies within here, if all of these dots represent every imaginable real value, right? And we call each value what? We call each of these values elements or members. And so we're saying that x is an element of that set means it takes all of these values. It can take on all of these values. X can take on all of these values. There's no restriction to it, right? And then the outputs that you can get, is what we call y elements of real, right? Because I can input any imaginable x value and I can output any imaginable y value. There is no restriction. And so this is why we say that the domain is x elements of real and the range is y elements of real. So what are the set of x values, or what are the set of inputs that I can use in this function? Well, it can be any imaginable real value, a value that exists. And what is the set or possible y values that I can output? It can be any imaginable real value. Can you see why functions are so important? Because we're starting to link number systems now to functions. And I did mention that all of this is going to tie in eventually. And this is where it's actually coming to play, right? So let's go over this again. The way we denote it, I want to say I can input any imaginable real value. How do I write that mathematically? It's just here. X is an element. Elements are the individual or distinct values that lie within a set. So if X is an element of that, means it can be any of these values, right? We're just saying it can be any, it's a part of that set. What set? The real number set, right? What is a set? It's just a collection of mathematical things or collection of numbers. And so when we're saying the real number set, we're saying it's a collection of real numbers. What are real numbers? It's basically every possible imaginable number, right? And then what values can you output? Are there any restrictions? No, there's not, right? If you don't understand why that's the case, take it as a rule. But if you think about it, I can input any value here. I can put in a fraction. I can put in negative values. I can put in 0. I can put in positive values. I can put in whatever values, surds, irrational, rational, all of that, right? Everything that comes with real, any real value I can input here, and I'll output some value of any of those nature, right? It can be real, it can be rational, irrational. We can go down the mind map, and you would see that it would give me an output. Okay. How to identify a function? A function must match each input to only one output. I've explained that using the basic definition of a function, right? If an input gives you more than one output, it's not a function. Now, this is what we will work with at grade 12. If you put an input and it gives you more than one output, then that's not a function. It's what we call a relationship, right? So yeah, this is why it's so important that you understand it. Now, these are this part here you won't ever be tested on, so don't worry about it. But I'm just expanding your mind and preparing you for higher grades. Okay, the next thing that we will work with is representing a function. So now that we know what a function is, how can we represent it? Remember, when I talk about representations, it's just different ways of saying the exact same thing. And so let's say, for argument's sake, that the mind map, this flow diagram, is something that resonates with you. When you're given the function in the form y is equal to 2x plus 1, and if this is a way that you can't understand or it doesn't resonate with you, these are exactly the same thing. And so you're literally thinking of it from the exact same perspective, right? And so this is what you can use as a useful tip. If this idea resonates with me, but I'm giving this, then I must think of this in terms of this, because it's the exact same thing, right? So if the equation is given to you, the function is given to you as an equation, right? But the flow diagram is the way that it resonates with you, then think of this equation as a flow diagram and then solve all your questions in terms of that, because it's the exact same thing, okay? So how do we represent functions? We either use a table, we represent it graphically, algebraically, which is this method here, or we use flow diagrams, right? The first two ways, algebraically, this is what we say algebraically, is what we will do at grade 10 and higher grades, right? What we call mapping notation and functional notation. Here at grade 9, we just use this here. Y is equal to 2x plus 1. Y is equal to x squared, or whatever it may be, right? So yeah, that's basically that, right? So you don't have to worry too much about it. But if you want additional information, basically what this means is we say f of x is equal to 2x plus 1. X here represents the input. This here represents the output, right? And f represents the name of the graph. So if I have to sketch this quickly, this graph will assume such a shape, right? The name of it, we give it a name, is called f, and x is obviously your inputs, and y is obviously your outputs, or f of x, right? So you can see here that f of x is the same as y, right? And 2x plus 1 is the function, okay? So f of x is y, x will obviously just be x because it's the input, and this is what we call the function, right? Because remember, the function is just made of what? Input, rule, output, right? So f of x, this whole thing here, is the output, x is the input, and 2x plus 1 is the rule or the function. Okay, right, so that's that. Right, so that's what we call the algebraic way of representing it. So that's one way. The second way is graphical. I've just done the graphical representation of it, where you actually go and draw the graph. Now I'll teach you exactly how we do that, but it's very simple, right? When you're just given a graph, when you can see a visual, then this is what we call the graphical way, right? So now you know the algebraic way, you know the graphical way. The way using the table is very simple as well. You have X, you have Y, you just list a few inputs, and then you get the corresponding outputs, right? I will do questions on this, but it's very straightforward. You can literally see it. Here as well, flow diagram, very simple. You have an input, you have a rule, and then you have the output. So I input 1 in here, what do I output? 3. I input 2 in here, what do I output? 5. Input 3 in here, what do I output? 7. 4 in here, what do I output? 9. Right? All of these are the exact same way of saying the exact same thing. Right? So we don't have to worry too much about it. Before we proceed with our discussion of functions, I have to mention the fact that with all functions, we have what we call a parent function, which is the primary function without any translations or transformations. It is this function that gives the definition to a linear, parabolic, hyperbolic, and exponential function. To me, the combination of functions and algebra helps you understand all other topics in maths. When you view the solutions in the example problems for algebra and the solutions to the DBE questions, you will see that I make use of functions extensively. Now, this is something that I taught to grade 10 students. But basically what I was trying to emphasize here is the fact that functions is literally the most important section in maths, right? And there's certain ideas that we need to use from functions that will enable us to solve much more complicated problems, right? It feels more anchored when you have a visual, okay? And then we have what we call a parent function, right? I've talked about this extensively on this platform, understanding definitions. When people say that, when people talk, they speak very abstractly. Like you can't really understand what they're saying because they don't understand the definitions themselves. And so when I talk about a linear function, right? When I talk about a linear function, most people just think of this here. Y is equal to 2x plus 1, right? Or y is equal to 3x minus 4. That's what they think about. But what actually makes up a linear function? What's the most basic definition of a linear function that gives meaning to the linear function, right? And what are some of the constraints that apply to this function? And so if I do this here, the most basic definition of a linear function is y is equal to x. This is what we call the parent. Think about this, the parent, the primary function. This is the basic definition. Why is this so important? Because I can add a number here, or I can add a number here, right? So I can add a coefficient, or I can add another term, a constant term, 2x, right? But if I change the exponent, then I am changing the function entirely. And so this is why the parent function gives the meaning to the linear function. It tells me what I can do and what I cannot do, right? And this is why definitions are so important, because they tell us the constraints under which a topic still applies. So if I, like I said now, if I change the exponent, I change the function entirely. If I put in 2 here, this becomes a quadratic function and not a linear function. If I put a 3 here, this becomes a cubic function and not a linear function. If I put a 4 here, this becomes a quartic function and not a linear function. So what are the limitations? What can I do? Right? At the extreme, what can I do with this? I can only change the coefficient or add a constant term. Do anything else to it, you're changing the function. We are not working with a linear function. We are working with something other than a linear function. Okay? So these are things we're looking at it from a realistic standpoint. And so when I discussed, or one of the guiding principles that we use here is we have definitions and standards, right? We have definitions and we have standards, right? And so once you have these definitions and standards in order, then everything else just becomes a re-representation of this, right? Or a re-expression or a variation of it. But the standard is the foundation for it. Do you understand what I'm saying? See, y is equal to x is the foundation for the linear function. If I put in a 2 here and I put in a 1 here, where did this 2 and 1 come from? It came from x. Y is equal to x. Do you understand that? So that's the basic definition. And so what we say is that we transform or we translate y is equal to x to get y is equal to 2x plus 1. We transform or we translate y is equal to x to get y is equal to 3x minus 4. Now, what translation and transformation means? Very, very technical terminology that I will get to and you will eventually understand at higher grades. Okay,